Hello everyone, how y'all doing today? We are going to be going through electric field 1 today. Simple concept, it's not too hard if you practice enough. And okay, so going into electric field, before we actually head into this one, let's explain what electric field is. So when I have an electron or a proton and an electron, you know how we said they attract? These arrows represent the force they exert on each other. And if they're the same, they repel. And that is also the force they exert on each other. Now, what is causing this force is the electric field. Now, what is the electric field? Every electron or proton, when you put it, it exerts some electric field. For a proton or a positive charge, it's away, and that's what it looks like in all directions, z, x, and y. And for a negative one, it'll be towards. All right. And so these are the electric field lines it creates. Now going to here, you see this is in 3D. As you can see, you see how it's towards it. That's an electron, negative. And if I reverse it for a proton, it's away. And it's in all field lines. All right. And now when I put two of them, as you can see, they affect each other. But since this is a little bit hard to see, I'm going to slice it in the Y. And you see, this is what it looks like. Ignore my cursor. I don't know why it's like this. But you see how I can actually zoom in. That's nice. You see how the lines are going towards it? The closer you get to it, the stronger the electric field is. And the further you go away, the weaker it gets. Until eventually, I don't know why this is. Okay, I guess not. Oh, there you go. Okay, so now what I want to do is I want to show you that if I put two of them, what happens. As you see now when I put two, can I move this? Ugh, I guess not. But you see when I put two, because they're opposite charge, you see these are both electrons. This is pulling towards the electric field, and this is pulling towards, you see as I'm moving it, it bends over. See here it goes down, and then it slowly bends over. And if I put it in the middle, see it's kind of just, if I go here. Okay, so I hope that kind of explains what an electric field is. There's a second simulation that actually explains it a lot better. And you see now when I put one charge, it's just all the way away from it. And when I put this charge, you see it's all towards it. Now if I put a positive and a negative, you see they connect. And so one thing, back to our notes, one thing is electric field lines can never be crossed. They always either connect. So if I have a positive and a negative, they will connect going towards the negative, right? Like this. Okay? And the back one's kind of like try, but it's too weak, so it goes like that. But they never cross. And if I have them opposites, and look how close I'm going to keep them actually. What happens is this will bend out of the way. It will bend that way. Because they can't connect. They're the same, right? And so what happens is the electric field lines want to straighten out. They want to straighten out, and that's what causes this force that pushes them apart. Imagine these are like metal springs, and they're trying to straighten out, and so they push on one another, and they force, they exert a force in the opposite direction, right? And you could see when I go here, if I take this and I put it here, you see this? Well, actually, this kind of explains it poorly. But if I go and I go electric field in 3D, and we can find like a same charge, as you can see. So you see this is opposite charge. You see how they connect like this? Now the same charge is, let me see where I can find a good example. Why is it all same charge? That's crazy to me. All right, I believe I saw one here, but it wasn't the best. Oh, there it is. Look at this, how it bends away because they're the same charge. Okay, and so that's how it actually works. That's an electric field line. And now this electric field is always exerted. Even if I have just one, it's going to create its own electric field, right? And so how do I measure the electric field that it creates? Right? If I want to measure it, how can I measure it? And so there's a formula. There is, actually I'll go to the side here. There's a formula. This is to measure electric field. And electric field is a vector, has a direction and a magnitude. And so it equals the force on that some charge, okay, over the charge. Now you're gonna be like, what is this guy talking about? Okay, so if I have some point charge here, positive, and it creates a electric field, right? Now if I want to measure the electric field it's creating here, what I'll do is I will put some little charge Q, right? It's imaginary. I'm gonna put some little charge Q, and I'm gonna measure the force this is causing on this. All right. So we know that our force equals K, Q1, Q2 over R squared. Let's name this Q1. Let's name this Q2. This is divided by Q1, by the way. All right. Now, when I put this equation on top of this equation to get the electric field at this point, what will happen is I will get K, Q1, Q2 over R squared all over Q1. And you see these two will cancel out, giving us K, Q2 over R2 equals my electric field. And what this means is this is basically telling me is that, hey, you don't even need to put this imaginary charge here. You can just use this equation. Like if I put a point here, all I need is the distance R and the charge, the charge of the source, right? And so that's my Q2. And this will give me my electric field. Now, this does get a little bit more complex when it comes to me trying to measure it for multiple charges. And that's usually where electric field 1 gets hard. But if you do a little bit of practice, you'll be fine, I think. Right? So now we are going to go into an example where, actually, before we go into a hard example like this, I'm going to go into an easier one and then slowly go into hard ones. So now that you know the theory and the math and the equation, all you need here is to do some practice, and that's what we're going to walk through. This one is pretty complex, so if you don't understand it, just wait a bit. What magnitude charge creates a 1? So your E is measured in newtons per coulomb, okay? And so what magnitude charge creates a 1? So I have my E equals 1. Electric field at 0.1 meter away. So my R is 1 meters, okay? And so what this is saying is I have some charge here. I don't know what the charge is, negative or positive. And what I do know is that some distance R away, there's an electric field that is 1. And so what is my charge? Well, here, as you pay attention, it says away. And remember how we said positive is away, negative is towards. And so the electric field this creates, since it's away, that means this is a positive. Now using our equation, right? Well, I gotta submit, I have my 1. So but let me rearrange. What I'll get is E R squared all over K. That'll give me my Q1, which is the Q here. And what I can say is, well, 1 R squared all over K. My R is also 1 meter squared, so it's gonna go away over K. That's my charge, right? And so that is our first easy problem. As we go, we're going to get a little bit harder and harder. So now what we have is a charge is located at X and Y. What are the electric fields at positions? So let's go slow. First, it says there's some charge is located at X and Y, 1 centimeter and 0 centimeter. So as soon as it says X and Y, draw your X and Y's. All right. Horrible line. Okay, so this is my X. That is my Y. This is my negative Y. And it's telling me there's a charge at 1 centimeter and 0. So 0 on the Y and 1 centimeter on the X. Right? And so that's where my charge is. Now it's negative charge. So this is actually, we'll put it in red. Negative charge. Okay? And this next charge, where is the electric field at? They want the electric field at x 5 centimeters. Okay, and they want the electric field at negative 5 centimeters, so somewhere here, right? And they also want it at 0 and 5, so up here. Now, I'm not going to go into these two because they're pretty simple since we just did it here. You know, this is, you just use E equals K Q over R squared. Your R is the distance between this, that's your R. Or the distance between this, that's your R. Your charge is obviously given, and we're looking for electric field. Okay, so now at this point, what is my electric field here? If I want to measure it, I'm going to redraw this. Okay, let's redraw this. What I have is some electric field here is what we're looking at. And we know that it is 5 centimeters high. All right. And we also know that across where our charge is 1 centimeter away. Right. What is the electric field here? So I know that my R is the direct distance, right? So my E equals K Q1 over R squared. Now keep in mind, your R is always a distance exactly between the 2 points. I cannot, let's say, so you know how the electric field here will push it that way? That's my E. Let's say I want my E in the X direction. This is a vector, so I can actually split it. I cannot use 1 as my R, because that's the distance between this and on the X. No. You have to find the R first, which is the direct E, then split it into X and Y's. Okay? And so now, let's explain this. By the way, this equation has something called a R hat. And what this R hat represent is this direction. So you know how this R, well, this is negative. This actually will be towards it, right? Yeah. So actually, let's rewrite this towards it. So let's do that. So my point I'm measuring here. And since my charge is negative, remember I said negative, the electric field is towards. So that is actually my electric field. And you see my R hat is in this direction. Okay, this is my R. R hat is just equals to 1. It just tells us direction, whether it's towards or away. Okay, and so now what I will have here is this R hat is negative because it's towards. It would be positive if it was away. Right, so keep that in mind. That's what R hat determines direction. Okay, now that you know this, we have my E, and obviously I have my E in the X, and I have my E in the Y. Okay, and so now how do I get my E? My charge is, so 8.99 times 10 to the 9 times my Q1 is 12 times 10 to the negative 9. And remember, I didn't put negative because this negative just tells me if it's towards or away, and I'm representing that using my R hat at the end. So direction, keep it in mind. Now what's my R? It's R equals the square root. I'm using Pythag here. Okay, but here's the problem actually before we do this. There's a problem when it comes to your units, is that my K value here, this K is equals to 1 divided by 4 pi epsilon naught. Epsilon naught is measured in farads per meter. And since this is in meters, that means everything has to be in meters. All right? Because your K is in meters. Okay, so keep that in mind. This is you could mess this up, and it's big difference in results, in like values. So make sure you get that right. Anyway, so getting my R, converting everything into meters. Right, and that's my equation. And now plugging this in the calculator, you'll get something. I'm just gonna plug it straight in here. There you go. And so this, after you calculate this will give you some E measurement, some number, right? I'm gonna plug into the calculator right now. But obviously I have to split it into X and Y. Now do you? Not really. But in this question, they specifically said, write in field vector in component form. Component form is what we said with the R hat, J hat, I hat, K hat. And what are these? I'm gonna explain what JI. So I hat equals positive X. That means negative I hat is negative X. That tells you direction, whether you're going in this way or that way. Alright? J is positive Y, and vice versa. Negative is negative Y. And K is Z. Alright? And same thing. Positive, positive, and then negative, negative. Okay? So now they want to start presenting it in this format. That means basically what they're trying to say is get my EX and EY. So my EX, using Python, now this is obviously some theta. Now we know that to get my EX, I can use cos theta equals adjacent over hypotenuse, right? And so my adjacent here is actually EY over E equals cos theta. Now rearranging, EY equals E cos theta, right? That's my EY. And that means my EX equals E sine theta. Now all you gotta do is plug in your E number, plug in your sine, but what's your theta? Now your theta, we do 10 equals opposite, so 10 of this angle equals opposite, which is my 1, over adjacent, which is my 5. And so rearranging, I believe this gives you something like 11.31 or something like that. Okay, so you take this, plug it here, you got your E from here, plug it here, you'll get your EY and you'll get your EX. The way you would write it for the answer, you would say my electric field equals whatever number you got from your EY or EX. You just gotta put a J hat in front of it. Now obviously both of these, my EX is going in the positive I. So this is actually in the I, and this is positive, right? Now this you do plus your EY in the J hat, right? But obviously we know what our EY is going downwards, which is negative. So if my J was negative, that means this will turn into a negative. And that's how you would write it. This is the format. Okay? So now that we did this, let's go to the next question, and then we're going to go into the rod one, which is the lengthy one, actually. Nice. What is my next question? What are the strength and direction of electric field? And okay. So for this part, all we gotta do is let's take our diagram here. All right, and then we're asking us is what's the electric field at this point? Right. Now the electric field at this point is, we know that this is gonna, here actually I'll use 2 pens, one green, one red. This is gonna be my green section, and when I'm drawing in red, I'm representing this section. Okay, so we know my green will exert a force, an electric field, this is R, and it will create an electric field this way, right? And this is positive, so it's away. And this electric field has an X component and a Y component, just like all the other electric fields. Nothing too special. Right? Now for my red, this guy is going to go all the way across from distance R, and is going to take it the same thing, but other way. Alright, so here, and that is my E, and same thing, it has an X and a Y. Okay, now as you can see here, the distance is 5 centimeters for both. The distance apart is the same, as well as their charge is the same. That means when I'm calculating these forces, my E here that's caused by this, and my E here that's caused by this will be the same thing. So that, what does that mean? That means their Y component will be the same thing as well. But one is pushing up, one is pushing down. That means when I add these together, it will cancel out. So that means my EY doesn't even matter because it cancels out. And that leaves me with my X component, which is added together. Now, how can I get my X? Same thing as we did in the last example, split into two parts, my E1 and E2. However, like we said, our EX, just like the EY, will be the same magnitude. So we only got to calculate it once and times it by 2. Or calculate it once and add it twice. And so e to the x equals k q over r squared. Now my r equals the square root of 0.05 squared plus 0.05 squared. Right, that's my r because I'm looking for this section and I gotta use Pythag here. Okay. Now, plugging that in, k is a constant. My q is 3 times 10 to the negative 9 all over my r, which is the square root of 0.05 plus 0.05. I don't know why I put that half-ass bracket right here. And this will give you your electric field. Remember, this is electric field. What I'll have to do is get my x. And if I'm using this angle, that is the same thing as this angle, or this angle, and this angle. And since these are all symmetric, all these thetas are the same. All right. So, but let's use only one. We'll use this one. All right. Now, how can I find this theta? I can just do 10 inverse 5 over 5 equals my theta, which equals 45 actually, because 10 inverse of 1 is 45, and that's your theta. Now, how did I get my EX? Obviously, my E is some number that I'm going to get from here. Then my EX equals E cos theta, just like we did earlier, because this is my angle, adjacent is EX, hypotenuse is E, rearranging, cos theta equals E. So you take this number and you plug in your 45, so this becomes your E cos 45. That gives you EX, but that's only for one charge. Since we have two charges and they're both in the same direction and the same magnitude, what we can say is it's actually this whole thing times 2. Or you can say my E, so my actual E is EX plus EX. Okay? Because obviously there's two EXs, you add them together, that's your E because your Y's cancel out. Alright? So that is this problem. Now going to the hard problem, and this is using two thin long glass rod. I'm only going to use one to explain this, and so let's use it. The problem states is that I have a long rod, so I have a thin long rod. This is also, I'm going to introduce you guys a new variable. Alright, before we do this problem, let me introduce the new variable real quick. Now, if I am going in 2D, and imagine this is very thin. It's so thin that it's actually 1D. And if this is charged with a lot of charges, positive, right? What I want is I want to find something called the linear charge density. Now, what does linear charge density mean? My mic closer because this is important. Oh, there you go. Okay. Well, linear mass density states, and it's used lambda, it equals the charge divided by the length. Now, what does this actually mean? Imagine I have this little square, and this little square has balls all across. Everywhere, okay? Now, these balls, when I fit them in, let's say these are like little magnets, or you can say these are little charges. And these charges, I'm not going to continue this, but these charges, the distance between them is even. Why? Now, you know how I said if I put two positives, they repel? But if I contain these in a box that's like this, then what happens is these will go to the edge. And so they'll actually move. They'll go here. Right? But what if I put two more? So I have this one here. And obviously, what the hell? Hello? And obviously I have this one here. Now, what if I add more? Let's say I add another one here, and add another one here. Now, this one is going to push on this, and it's going to go somewhere down here. Jeez. Come on, dudes. We'll go somewhere here. And obviously, this one will also go down here because this is forcing it down. But then these will force each other, and so they'll go to the corners. Now, what if I add even more? What if I add another one in the middle here? Will this go anywhere? The force that's pushing it up is the same force that's pushing it down. And the force that's pushing it left is the same force that's pushing it right. They'll stay there. But what if I add one more? You see now, what they'll look like is something like this. Because these two forces are pushing it in, these two forces are pushing it in, but these two are also repelling each other. And so when I add an infinitely amount of charges in there, then they'll just squish, and the distances between them will just even out. And so wherever I look, there will be the same amount of charges in a certain space. And so if I take all these balls and I divide them by the area I have, it will give me some ratio that will tell me how many charges I'll have at a certain location. And so if I look here, my lambda, my density is the same. And if I took even a small portion, it's the same density. And if I took the whole thing, my lambda will stay the same. And so that is your lambda. It says linear mass density. All right. Now, this doesn't only work with linear, because what if I had a plane, like a square or a piece of cloth, and I also filled it with charges? Then this is, you could say, I believe this is denoted by some thing that's like that. And this is area. And this is not mass, by the way. I don't know why I wrote mass. This is charge. And so area, charge, density. And the way to calculate this, it will do Q over A this time. And if you have a 3D, right? If you have a 3D object, and so this is 1D, this is 2D, and 3D. I believe this is eta. I'm not sure what this one is called, but this one is just Q over V, and this is volume, charge density. All right. So if this is all filled with charges, this is how you calculate it. All right. So now that we know what lambda is, let's go here. What is the problem with this? This has some length. Oh my God, that's horrible. All right, this has some length L, and what we have here is, actually, before I get here, let me put my charges. So this is, let's say I charge it all positively. Okay, and now I want my point charge that is right in the middle here. Not point charge, but what's my electric field here? And so this is some distance away. Some distance d away. All right. Now, how do I calculate this? Remember how I said if I have a charge here and I have a charge here, and I'm trying to calculate the point charge here, then what I'll do is first I'll split it into this problem, calculate my electric field, which will be this way. Then I will create it into this problem, split it into another problem, and this one will be that way. Then I'll take these two vectors, get my x's and my y's, add them together, and that'll give me my, which would be an electric field this way, right? And that'll give me my sum. And so here we can do basically the same thing. But the problem here is there are so many charges. I don't have time to do it for every single one. And so this is where we're going to use integrals. We're not going to be integrating, but we're going to be using integrals. All right. And so let's first split this into small charges. And so small portions. So let's say we take this one portion, right? Now, what I'm going to do is I'm going to calculate, and actually I'm not going to take it at the end because I want to explain some phenomena. And so I'm going to take it somewhere in the middle here. All right. Now, what I'm going to do is I'm going to be like, okay, let me calculate this one, and then I'll worry about all the others later. And so if I want to calculate this one, I have some theta here, I have some r distance, right? And the electric field caused by this is away. Something like that. And that is my E that is causing, right? And obviously, this E is split into two vectors, my X and my Y. Okay, now first I have to think a little bit ahead because I'm going to chop these off and calculate them one by one and add all these forces together. If I do this section, right? If I do this section right here, this will push it that way. And that is the same problem we had earlier where you see my X is this way and my X here is also that way, except my Y is upwards. And so this Y and this Y will cancel out because I'm right in the middle. That's symmetry. Okay? And so my X and Y will cancel out. Sorry, not my X, my Y and Y will cancel out. And so that takes Y out of the way. And so what I have is just two X portions. I don't have to add them together. But right now I'm only going to worry about one of them, and then I'll add the second part to it. All right? And so now let's take this. This is the half point, right? We're going to name this point 0. Okay, this is 0. That means this is negative L over 2. Remember, this whole thing is L. If I set this 0, so that's 0 to negative L over 2, and 0 to L over 2, right? Because this is half L, so this is L over 2. Hope that makes sense. Okay? Now, if this was a point charge, and I'm trying to find the electric field here, what I'll do is, obviously, this is my R, and this is my electric field. This is my EX, this is my E, and I have some here and something here. All right, this is my theta that we did earlier. This is theta that we did earlier, and my equation is E equals K Q over R squared, which would be fine for this problem. And since I'm also only looking for my EX, we know that my EX equals K Q over R squared cos theta. Now, why did we do EX? Like we said, because the EYs cancel out. So we're only going to take our EX. So now what is my EX when it comes to something like this? Obviously, we have the charge. We have some angle theta, and we have some component R, some distance R. Now, when I'm looking at this, as I go down and I calculate and add up all the different electric forces at each point, my R will change. The R here is different than this R. It's actually shorter. And so R changes. So let's keep that in mind. R changes as we go down. Okay? My theta also changes. You see, as I'm going downwards, as I'm going down, the theta changes. The theta also changes. Okay, so that's problem number 2. Now, what is my Q? Remember, I have some letter Q. And does this represent the whole rod? And the question is, well, no, we can't really calculate the whole rod because the electric field that this causes is small, while the electric field this causes down here is bigger because obviously the distance is closer. So, well, my dq is going to be some charge. I don't know the charge, right? I'm taking some small piece. I don't know the charge for it. But what I do know is, like we said earlier, my lambda equals Q over L. And like we said, if I have a box full of charges, my lambda will be the same if I calculate for the whole box or if I take a small portion. The density is the same everywhere. And so, well, we have that in common. So how about we use that to our advantage? I'm gonna call the charge here dq, and I'm gonna call the length of this. Let's assume this is a tiny rod, and this rod has some charge dq, and it has some length dy, right? And we're like, okay, then, well, my lambda is Q over L, and this Q is for the whole rod, all right? This is for the actual rod. And so my Q for the whole rod is just, so let's say, rod charge equals big Q, right? And so it's Q over L. And I'll be like, okay, well, I have a second rod. This is my second rod, which is lambda equals dq over dy. All right, I could have said it's x over y. Like this is, I just named it dq, right? And this will connect why we named it dq, but for now, just think about it as something I named at random, right? And so, like I said, well, earlier we said, well, lambda doesn't change. The density stays the same because the electrons don't move. And so if I take how dense is it at some point, or how dense is it in the whole thing, it's the same density. And so, well, then this equals this. So as you can see, well, can I rearrange and get my dq? Lambda dy equals dq. And my lambda, I got it from here. And I can't calculate it. I have my length, I have my q. But here, I don't have my dq. I don't have my dy. But at least I have my lambda. So, why do I want this in terms of dy? Because since, remember how we said the problem is my r changes and my theta changes? And now we have something called dy. And as I'm going down, well, this dy doesn't necessarily change, but how to calculate my dy changes. And so the problem is, how do I get my dy? And so what I'll say is, this is my y-axis. This is my y-axis, right? And this is my negative y-axis. Okay? And so the change dy means the change in y. And so how can I get a consistent dy? Is that if I take this y and I minus it from how high up I am, well, if I take this and I minus it from this, then I will get this portion, which if I were taking the whole thing. So what I can do is, name it so that I'm taking the change in y, which is from up here to here. And if I calculate these two, I get the same dy. And as I go down, this changes. And so, well, that is a good thing. And why is that a good thing? Is because we can actually put everything in terms of y. How does that work? Well, since everything changes, I can't really integrate and add all these little charges because I have too many unknowns, and all these unknowns are in different variables. But if all these unknowns were using the same variable, then I can just integrate it. And so now let's integrate. What I'll see here, this is my equation, right? My q, now what I'm doing is I'm taking the charge that this is causing, which is dq, all over the distance away, which is r squared, cos theta. Not much changed yet, but, well, let me change my dq in terms of y, and, well, this is valid, so mine as well. Lambda is a constant, it's given, right? Because I can calculate it. And so, but my dy is not, so I'll just keep my dy for now. Now, how can I get my r in terms of y? Well, d is a constant, that's given, and this is my y. So, well, in that case, I can get it in terms of y. And so, how can I? R equals Pythag, y squared plus d squared. Well, now that's also in terms of y, which is great. Let me plug it in. And so I'll get y squared plus d squared. Now, there's a squared here, And there's a square root here, so they cancel out, leaving you with just a naked looking y squared plus d squared. Now, what about my cos? Well, I know cos theta equals adjacent over hypotenuse. So what's my adjacent, what's my hypotenuse? Well, if this is my theta, my adjacent is d and my hypotenuse is r, so let's plug those in. Well, we have d and we have r. D is a constant, so that's fine. My r is not, but we just solved r in terms of y, so let's do that. And dubs. Now, if I plug those in, as you can see now, everything besides y is a constant. And that's a good thing because, well, I also have my square root here. And that's a good thing because now I can actually integrate this. And so if I put this all together, a lambda d, all these are constants, right? And I have my dy, which is this one, divided by, if I combine these two, this is saying, right, this is to the power 1 times the power 1/2, because this is like the square root, which is 1/2. When you add these, when you add 1 plus a 1/2, you get 3/2. And so if I were to rewrite this, I get 3/2. And this is very simplified now. All I gotta do is, well, now I can integrate actually. And so my EX, obviously here, the EX that this is causing is DX, just to put everything consistent, right? Because we have DQ, DY, well, this is also DE, and this is also DEX. And so here we'll have DEX, and now I can actually integrate both sides. Now, all these are constants, so they'll stay on the left side. But the question is, well, what are my bounds? Where am I taking it from? And, well, obviously, I'm taking it from negative L/2 all the way to L/2. And so, now you might think, well, yo, before I actually do this, can I just integrate from 0 to L/2? And then whatever result I get, I times it by 2. And actually, yes, you can. And so that is another way you can do it. But you cannot do from 0 to L. Reason being is because our y goes from the middle up there, because as the y goes on the other direction, a couple things change. And that's why you want your 0 to be right in the middle. All right. Now we will go into some instances where we will using the whole rod, but the point charge will be like down here. And so we can use the whole charge, we can integrate from 0 to L. But for now, just keep it how it is. All right. And so now we're going from negative L to L. We want to integrate this, your integral here. This will be given on a test. Right. So the integral of this will be given on a test. And if I can remember it, this would be d squared square root y squared plus d squared. And that's what it looks like. And don't forget, we're taking it from negative L/2 to L/2. Now, all you gotta do, you have your L, you sub it in, you sub everything in, and that would be your answer of what electric field this rod is causing at this point. And now, I hope this explains this unit better. We are going to be doing some more examples of a little bit more complex examples in a bit. And so I'll see you guys on the other side.